Good morning and welcome to this summer school. That's my welcome, although too late. So yesterday, you might have not noticed, but we have transitioned to multiprocessors from uniprocessors, and we'll continue that thread today. So the first hour will be spent understanding something called cache coherence, which I have decoded a little bit for you, which is the architectural supports for efficient shared memory. You have seen what shared memory is yesterday. And we'll spend the next hour understanding something called memory consistency models, which will take you to some thorny aspects of shared memory programming. So you'll see when you get to that. So this is the rough agenda of what we're going to do in the first hour. I'll spend one slide just recapping what we saw about shared memory yesterday. That's the software side of it. And I'll spend a few slides understanding what hardware supports shared memory, that is shared memory multiprocessors, what they look like today. And then we'll jump into discussing what cache coherence is. And I'll represent cache coherence as a set of invariants. And we'll see how to implement those invariants. And as long as we implement those invariants, you'd have an implementation of a cache coherent multiprocessor. So that will be the philosophy of the lecture. And we'll look at a couple of cache coherence protocols, which are very basic, MSI and MESI. I'll explain what those M, S, I, and E things stand for. And if time permits, we'll close with a few formal definitions of cache coherence, which are just for formal purpose. Otherwise, if you want to get into formal verification of coherence protocols, they may be important. And please feel free to interrupt me at any time. So what is shared address space? Well, part of address space is shared between multiple threads or processes. That's what we understand when we say the address space is shared. And this can be achieved in multiple different ways. You'll see one possible way today when you write some parallel programs. For example, this can be achieved by declaring shared variables as global for sharing among threads within a process. So this is the POSIX thread model. And what we'll see today is a stylized wrapper on top of POSIX thread model, which is called the OpenMP standard. So you'll be writing programs using that. But underneath, this is what it does. It declares certain variables as globals, which become shared across threads within a process. Or it could be achieved by allocating memory through specialized system calls for sharing among different processes. For example, you could use Unix SHM get or SHM at calls. If you don't know, don't worry about that. But that's how you share memory across processes if you want. Okay. So first one allows you to share memory between threads of a process. Second one allows you to share memory across processes. Yes? They're not, yeah. So yes, they're not part of the POSIX standard. Yes, so they are system 5. Say again, sorry. So the actual POSIX standards were SHM. Yes, that's right. Yes. But POSIX thread model builds upon a system call called clone in Unix. So that gives you the how to create threads and all these things. So we'll not get into those things. So this is just one slide explaining the software side of it. And variables in the shared address space can be read from and written to by multiple different threads and processes through standard load store instructions. This is absolutely important. That is, when you write something like x equal to 2 in your program, and x is a shared variable, it translates to a store instructions. Nothing more than that. Okay, all right? So it's a very lightweight way of reading or writing from or writing to shared memory. Okay, all right. Similarly, if you say y equal to x, where x is shared, you're reading x, it translates to a load from the address where x is residing. Okay, all right. So this is a very nice mode of communication between threads or processes for exchanging results. For example, a particular thread could produce x, and some other thread could use it for doing some computation just through load store instructions. Okay, all right. So of course, underneath, a lot of things are happening, and that's what we're going to discuss today, that how exactly are threads write is getting visible to some other thread, which can use those results. Okay. Now, shared memory multiprocessors are platforms to schedule in parallel multiple threads or processes that share memory. The in parallel part is very important, meaning that these threads or processes will run together at the same time. Okay, all right? It's not like time-shared concurrency. Okay. And many different designs exist today for shared memory multiprocessors. We'll assume that each processor has a hierarchy of caches, part of which is possibly shared between processors. Okay. For example, a particular design which has a part of hierarchy shared is popular in chip multiprocessors or CMPs. I'll show you how a typical CMP looks like today. Or the entire cache hierarchy of a processor could be totally private to it. Okay. So that's called a private cache hierarchy, found in some CMPs, which are sort of old today. This was very popular in symmetric multiprocessors of old times, which are called SMPs, and multi-node servers, where the cache is totally private to a particular node. Okay. So again, I'll show you some pictorial views of these things. And the third one is distributed shared memory, very popular in medium to large scale multi-node servers. And so this is what it looks like. So this is a shared cache architecture where you can see 4 processors, P0 to P3. Okay. Each has a private cache hierarchy. Let's see where the pointer is. Yeah. So this is a private cache hierarchy. This could have multiple levels of caches. Okay, all right. So I'm not showing that. And the last level of the cache is shared by all processors. And each processor with its private cache hierarchy connects to it through some interconnect. And you have seen a lot of interconnects yesterday. Okay. You can implement many of them on chip. Okay. And then the shared cache talks to your DRAM, which you have also seen yesterday. And part of the DRAM could be configured as a cache. That's also possible, which could be another level of your cache, which is built out of DRAM, specialized technology, slightly different from your commodity DRAM. Okay. So this is what a shared cache architecture looks like. That is part of the hierarchy. Cache hierarchy is shared. Okay. All right. This is a private cache hierarchy machine. And as the note says here, it may or may not be a single chip, this whole thing. Okay. It could be a single chip. For example, this chip could have 4 processors. Or it could be 4 processors standalone sitting on a motherboard. This could be a motherboard. That would be a symmetric multiprocessor, each having a private cache hierarchy connecting to over an interconnect to the DRAM. Okay. All right. Or each one of these could be a node individually connecting over an interconnect to some DRAM hierarchy. Okay. All right. So all these are possible. So, but the point here is that each processor gets a private cache hierarchy, and no part of the cache hierarchy is shared. Okay. And finally, this is distributed shared memory. And as the name suggests, we have brought the DRAM up here and have distributed it across the nodes. The DRAM is still shared. The entire memory is still shared. That is, this processor can access anything here, but the memory is distributed over the interconnect. Okay, all right. So to go from here to there, you'll have to travel over the network and get to that point. Okay. So you have seen all these architectures yesterday. All right. So these are the 3 possible shared memory architectures available today, and we'll not be focusing on any of these in the rest of the lectures. We'll be abstracting away everything. Okay. What we care about is that processors having bunch of processors having their own caches, and the address space is shared. That's what is important to us. How exactly that is implemented is not that important in the rest of the lecture. But I just wanted to put this in perspective so that you know what shared memory machines look like today. And there are machines which are called distributed memory machines, which do not have shared memory. And here, what you do is you pass explicit messages between nodes for data exchange. So now, these load store instructions are no longer sufficient, because if I want to, if this processor wants to load a piece of data that is residing here, it cannot just do a load instruction, because it cannot name anything here, because it's not shared anymore. Okay. So what you have to do is that you have to pass explicit messages from this processor down to this memory somehow and get the data and get it back here to the cache. Okay, all right. So that's called a distributed memory machine and will not be discussed in this session. A bit has been discussed yesterday evening, so we'll not be focusing on that at all. All right. So let's try to understand what really this term cache coherence means. Processors employ private caching of data to improve performance. That we have seen, and you also understand that because of caches, we can bring some data close to us, anticipating further reuse of those data, and caches can offer fast reuse. Okay, so that's why caches are important. Okay. So private copies of shared data must be coherent, right? So that's what we understand. For example, if this variable is x, if this variable x is shared, and there are two processors, P0 and P1, both of which are accessing x, and both of which are modifying x, we want to make sure that the values that each one sees is quote unquote coherent. Okay, that is, sort of see the same value. Okay, all right. So we'll formalize that notion. What exactly is meant by coherent? Okay. So roughly speaking, although this is actually wrong, all copies must have the same value. Okay, and it's enough if this holds eventually. That is, eventually the copies of x will have the same value. Okay, all right. So we'll again see what that eventually essentially means. Okay, we're not saying that this guy writes x equal to 2, immediately this guy will see x equal to 2. May not be. For a while, this guy may continue to see x equal to 3, which was the old value of x. That's still okay, all right? So we'll soon formalize what is okay and what is not okay. Okay. But this is what roughly we're talking about. For sequential programs that we write day in, day out, memory location must return the latest value written to it. That's what you understand. Like, for example, if we didn't have P1, we write 2 to x. When we execute this statement, we want y to get the value 2, because that's what x should return, because that's what we have written to it last time. All right? So that's easy. Now, for parallel programs, we expect the same, provided latest is well defined. Okay. Because let's say P1 says x equal to 5. Now, it's no longer clear which one is actually latest, 2 or 5, when I get to this point. Okay, right? So we need to formalize that notion, that what is latest. For now, latest value of a location is the latest value committed by any thread or process. For example, if I have a clock, which is a global clock, and if the global clock says that, well, x equal to 2 committed after x equal to 5, then 2 becomes the latest value of x. Okay, all right? So that's what we mean by latest. Okay, for now, that's what we're going to assume. Okay. And you understand what is meant by committed, same as retired. Okay, so you must have seen these terms, right? That retiring a particular instruction and so on. Okay. A cache coherence protocol is a set of actions that ensure that a load to address A returns the last committed value to A. Okay, I still keep last committed within quote unquote, because we'll formalize that very soon. Okay. So let's run over an example, okay, to see what we really meant. So let's assume there are 3 processors with write-through caches. Write-through caches has been discussed? Good, okay. Which means whatever I write to the cache will also be written to the next level of the memory, which we're going to assume the DRAM. Okay, all right. So let's say P0 reads x from memory, puts it in its cache, and gets the value 5. All right. So that's the first action. Okay, so we have P0 sitting here with its own cache, and in the cache we have x equal to 5. Okay, and there is memory here, which is shared by all processors. Then P1 reads x from memory, puts it in its cache, and gets the value 5. Must get the value 5 because x is 5 here. Okay, all right. P1 then writes x equal to 7, updates its cached value. and the memory value. It's a write-through cache, so it makes it 7 and must write through to memory, so this becomes 7. All right? Now P0 reads X from its cache and gets the value 5. Makes sense, right? Okay, because it's in the cache, so it should get the value 5. I mark it in red because this doesn't seem quite right. Okay, so P1 has the value X equal to 7. Somebody else is reading a wrong value. Okay. Now this may still be correct. Okay, but we'll formalize that notion. I mark it in red because as far as our mind goes, sequentially, it doesn't seem right. Okay, because a different value of X has been committed by a processor. I cannot see the old value. Okay, all right. P2 now reads X from memory, puts it in its cache, and gets the value 7. Must get the value 7 because that's what is in memory, right? So now the system is completely incoherent because now we have 2 processors with X equal to 7 in the cache, 1 processor with X equal to 5 in the cache, memory having X equal to 7. And now to make things even worse, P2 decides to overwrite X, makes it 10, and updates its cache value and the memory value. So all your processors now have different values of X in their caches. It's all messed up completely. Okay, all right. So the cache coherence protocol will try to make them coherent. That is, eventually they must have the same value. All right. Okay, and the eventuality window depends on many things. We'll formalize that. Okay. So that was about the write-through cache. Now let's run the same example with the write-back cache. Okay. So in this case, what will happen is that P0 will have the value 5, P1 will have 7, P2 will have 10, and the memory is not going to have the up-to-date value, right? Okay, so that's going to be the difference, and the memory is going to have the old value 5. Okay. And what are the states of the lines in P1 and P2? So you must have seen the modified state of the cache blocks, right? Huh? Dirty state, right? So that's what by M I mean modified, same as dirty. Okay, all right. So since P1 and P2 have modified the value 7 and 10, they will have the state M, right, in their caches. And P0's line is going to be clean. By clean, I mean that it's not being modified. Okay, all right. So now, since it's a write-back cache, eviction of the line from P1 and P2 will issue write-backs, while eviction of the line from P0 will not issue a write-back, okay, because clean lines do not need write-back. By write-back, I mean sending the data. Okay, eviction of clean lines may require some information conveyed, but we'll assume that data is not sent on a clean line eviction because it's not needed. Okay, all right. So if I assume that P2 evicts the line first and then P1, you can see that the value that X is going to get in memory is not going to be the latest value of X. Okay, because first what we'll do is that 5 will change to 10 because P2 evicts the block first, and then it will change to 7, okay, when P1 evicts the block. Okay. So final value in memory is going to be 7. Effectively, we lost the store X equal to 10 from P2. Okay. So memory essentially doesn't know about it anymore. Okay. It has overwritten that value. Clearly wrong, right? So let's see what went wrong. Let's try to recap and try to figure out. So for the write-through cache, the memory value may be correct if the writes are correctly ordered. That is, when you do a write-through, if you make sure that they go in order, the final value of memory is going to be correct. Okay, so that's guaranteed. But the system allowed a store to proceed when there is already a cached copy, because we said that P1 will change X while P0 is caching a copy of X, which created a problem, because later P0 read a wrong value of X. Okay, right? So lesson learned. We must invalidate all cached copies before allowing a store to proceed. If we do that, then that would make sure that when P0 tries to read X, it will not get it in the cache. That's it. Okay. It must go to memory and get the correct value. all right? So that will ensure correctness for the write-through example, okay? Now, for write-back cache, the problem is even more complicated because stores are no longer visible to memory immediately. They are cached, and only when the block is evicted to memory, it will become visible to memory, okay, all right? So suddenly the write-back order becomes important. That is, in what order the processors are going to evict the blocks, okay, to make the memory correct. And clearly you can imagine that that's going to be very difficult to ascertain because processors are free to evict blocks depending on the replacement algorithms in the cache. And it's impossible to enforce a particular order of write-backs across the system. It's very difficult. So lesson learned, do not allow more than one copy of a cache line in M state. Then you don't have to worry about the write-back order because there can be only one write-back if there is only one copy of the line in M state, right? So any questions so far? Okay. Sorry, second. Entire system. A cache block can be in M state in exactly at most one processor. Okay, all right? Yes, right. So how do you implement these lessons that we have just learned? So first, let's look at this particular lesson. That is, you must invalidate all cached copies before allowing a store to proceed. Okay, let's see how to implement that. Okay. So clearly, you need to know where the cached copies are to be able to invalidate them. Otherwise, there is no way to invalidate them, right? So solution one, you just go ahead and tell everyone that you're going to do a store. Simple. So all the processors will hear from you that, hey, I'm going to do a store. And the action is that, please go ahead and invalidate your copy, all right? So that leads to a broadcast Snoopy protocol. That's the term used, okay? And the name comes from the fact that you will broadcast a piece of information to everybody, and everybody will snoop on that information and act on that, okay, all right? Popular with small-scale machines because scaling broadcast traffic is very difficult for large-scale machines. Typically, the interconnect is a shared bus. However, AMD Opteron implemented it on a distributed network, the celebrated Hammer protocol, which we'll not be discussing here, but I just wanted to mention it, that it is possible to implement broadcast protocols on distributed networks. Second solution is you keep track of the sharers and invalidate them when needed. That is, as and when somebody requests a copy of the block, you keep track of that. That is, who is having which copies cached. Okay. So the obvious question that arises is where and how is this information stored? You have to store this information somewhere, right? And how do you store it? So this leads to something called directory-based scalable protocols, which avoids the problem of broadcast traffic in the other type, because here I exactly know where to send these invalidation messages, all right? So remember that these messages are not being sent by your program. It is sent by a hardware layer which implements these protocols, okay? You will be doing a load only or doing a store only, okay? And the store will translate to these invalidations to the cached copies. Somebody will figure these things out and will send out the invalidations. So let's look at the directory-based protocols a little more closely because a couple of questions pending, that is where and how we should store this piece of information, that is who is caching what. So normally, one directory entry is maintained per memory block. This is the simplest possible implementation that you can think of, that for every memory block, you attach a directory entry, and each directory entry contains a sharer bit vector and the state bits. So the length of the bit vector is equal to number of processors in the system, and whenever somebody caches that particular block, you'll set that corresponding bit, okay, all right? So, so that by looking at the bit vector, you know exactly which processors are having a copy of that corresponding memory block, okay? And you have state bits, which will also encode the states of these blocks. That's modified, clean, and many other states, which we'll enumerate very soon, okay? So, so let's now go back to our representative architectures and ask the question that where should my directory be? So these are distributed shared memory architecture. If you recall, we just discussed. Each one of these is an isolated node having a processor, a cache hierarchy, a DRAM, connected over an interconnect, all right? Of course, P0 could also represent multiple processors. That's also possible, all right? Residing in a single node. So, so the question that we ask here is where and how would you place the directory? Okay. So before we answer that question, we need to introduce a new concept called the home node. So in these architectures, what really happens is that you can see that the total address space is divided into these DRAM modules. Okay, all right. For example, if I have a 4 gigabyte of address that we can share, then each of these DRAM modules is going to be 1 gigabyte. Okay, all right. Very simply speaking. So if a particular address resides in a particular DRAM module, we say that that particular node is the home node of that address, all right? Because you can see that every address can reside in a unique node in the system, all right? Because there is no question of replicating an address across DRAMs, okay, all right? So for a particular address, the home node is the node where DRAM will have a copy of that block, okay? Is that clear, the definition of home node? Okay. And it makes sense to also put the directory of the blocks in a particular node in the home node. Like for example, whatever 1 gigabyte of address that this DRAM is holding, I would put the directory of that 1 gigabyte by the side of this DRAM. Okay. The other gigabyte directory entries will be residing in this node, and so on. All right. So that makes more sense because the directory and the corresponding block will now be co-located on the same node. Yes. Address will be? Address will be different in DRAM. Well, as I said, if I have a 32-bit address, let's say physically addressable memory, where 4 gigabyte of memory is installed in my machine, I would typically equally partition that into 1 gigabyte ranges. Okay. So it's totally mutually exclusive. All right. There is no overlap at all. Okay. All right. And for each 1 gigabyte, the directory will be placed here in the same node. Okay. So that I can go and access the directory and also read my memory block maybe simultaneously if I want to. All right. Okay.
So if the directory is placed in one of the nodes, then we are prioritizing it. So like,
sorry, second. If the
we are prioritizing a node if we are placing the directory in one of the nodes. So isn't it a bit unbalanced?
prioritizing means?
Like we're storing it within some node. So like
Correct, correct. For example, let's say address of X resides in this node, address of Y resides in this node. So directory entry of X will be here, directory entry of Y will be here. Yeah. So is that clear now? Okay, good. So what is the advantage of doing that? Well, that means I don't have to traverse the network twice, once for reading the directory, once for reading the memory block. Okay, because now they are residing in the same node. For example, if P0 wants to access, let's say, a variable Z, which is residing in this node, it will go here, look up the directory, and look up the memory block. Okay. And the directory will tell it what to do. For example, Z could be residing in this processor's cache. Okay, so we'll do something to get that copy. Okay. We'll discuss that very soon. So is it clear that the directory should be co-located with the blocks? Any question on that? Yes, as I just mentioned, directory is going to have two pieces of information. One is a sharer bit vector, which tells you who all are sharing this particular block, and it will tell you the state of the block. That's right, yes, yes. So every block is going to get a directory entry, yes. So it's a table as high as number of blocks in your per node DRAM. Okay, all right. So that's the simplest possible implementation. I'm not saying that that's what is done today. But let's start there. Okay, so is this clear? Okay, all right, good. The other one was the shared cache architecture, and we can ask the same question. where and how would you place the directory? What do you think? Shared cache? Why is that? Why not put the directory here by the side of the cache, private cache? Huh? Sorry? Yeah, right, it will be closer to the processor, right? Why not do that? Can have what? Okay, so one problem that has been pointed out, if I put the directory close to the processor, is that I may have to replicate the entire directory for each processor, okay, which may actually waste a lot of space. Okay. So one thing to notice before answering this question is that the directory that we're going to place here is responsible for tracking the blocks which are residing here. The directory has nothing to do with the blocks that are residing here. Okay, all right? So all we need to know is, given a block, is it cached in one of these? Right? That's what we want to know. So, so normally the directory is placed here by the side of the shared cache. Okay? And the directory should be ideally large enough to be able to track all blocks that could reside in these caches. Okay. So that given a block, if I ask, tell me which processors are caching this block in their private cache hierarchy, it should be able to give an answer. Okay, all right? Unfortunately, that could be gigantic, okay, because if you take standard sizes of these private cache hierarchies and multiply that by the number of processors, you can have a very large number of blocks. Okay. And putting a directory of that size on chip may not be feasible, okay, particularly when the number of processors or cores increases. Okay. So what is normally done is something called a sparse directory, or sometimes called a snoop filter. So what it does is that it caches, so this is also like a cache now, okay. It caches a subset of blocks that could be here, okay, all right? And it can exactly answer queries about the subset that it is caching, okay, all right? And the subset that it is not caching is problematic because you don't know anything about them, okay. So one option is that whatever the sparse directory can track will be cached here. You can't cache anything else here because you don't know about those blocks, because the sparse directory cannot answer queries about those blocks. Okay, all right. So that's the simplest possible implementation, and that is often done, and we'll stick to that. So is the notion of sparse directory clear? That it is essentially tracking a subset of blocks that could be cached in these private caches, and can tell you where these blocks are. Okay, all right. Clear? Okay. So you're asking the hard questions now. No, it's not, because this shared cache is never a monolithic single blob of cache. It's normally banked, and each bank will have its corresponding sparse directory. Okay, so that's normally how it is designed. Okay, all right. Yeah, it's all similar. It's just the technology is different. Yeah, they look very similar from high level. Yes. That's right. Yes. Yeah. This technology is also different. This is built out of something called static random access memory. Okay. So yeah. All right. So so the next question that we need to answer. So now we have settled the question that when I'm doing a store, how to invalidate the copies. Okay, that answer has been sought out. The next question is, the next requirement was that you do not allow more than one copy of a cache line in M state. All right, so two processors trying to do a store to the same cache block should not be allowed. Okay, right? So if you think about it, this is some form of access control that you require. Okay, that if two guys are trying to do a store to the same cache block, you have to somehow disallow that, or maybe let them do it one by one, okay, not simultaneously. Okay. So before a processor does a store, it must take permission from the current owner of the block, if there is any owner. Okay. So who is the owner? Well, he is the god of this block. Okay. If you want to do a store, you must take permission from the god. Okay. So the obvious question that arises is need to know who the current owner is, right? Otherwise, there is no way. Who is the God? That's the question that you have to answer. And answer is going to be either a processor or main memory. For example, if the block is cached in some of the processors, one of them could be the owner of the block. Okay. If the block is not cached by anybody, then main memory is the owner of the block. Okay, all right. So here also, for locating the owner, that those two solutions apply. That is, in the first solution, you could ask everybody, hey, are you the owner of the block? If yes, please do something, right? Okay. Second solution is that your directory could track the owner. Okay. The directory entry could have an owner field and could say that this guy is the owner for this block. Okay. So you know exactly who to tell when you want to do a store or when you're seeking a permission. Okay, right? So the point is that once you have found out who the owner is, so remember that the situation we are talking about is that there are two processors, let's say P and Q, that are trying to do a store to the same block X, right? Okay. So the typical way of doing it is that you will allow one of these to go through first. Okay. And who is that? Whoever will reach the directory entry will get the ownership of the block first. Okay. So that's the typical protocol that is followed. So P and Q both will send their stores to the directory entry of X. Whoever reaches first will be allowed to do the store. Okay. And once the store is done, let's say P wins the cache block. So the cache block X will now become modified in P's cache, right? And whoever is holding a modified block is normally the owner of that block. Okay, all right? So next, when Q is allowed to do the store to X, it will first find out who the owner is, and we know how to do that now, okay? Either from the directory or by asking everybody, okay? And once you have done that, this is important. That is, the latest value must be propagated to the requester. Okay? That is, once you have found out the owner must supply the block with the latest value of X to Q. Okay? All right? So that's how the exchange will take place. Okay? So how do you do that? So here again, notion of latest is very fuzzy, but I have actually just defined what is latest, if you have noticed. I said that whoever is going to reach the directory first is going to win the race. Okay, all right? So whoever was the last one to get to the directory is the latest copy producer, okay, if you're doing a bunch of stores, all right? So once we know the owner, this is easy. You go and get the block from the owner. So again, here, solution 1 and 2 will apply. That is, you either tell everybody and the owner will supply the block, because when you tell everybody, it will go to everybody, okay? And owner will see that, well, I have this block in modified state, so it will supply the block. Or you exactly tell the owner by looking up the directory, and the owner will respond back to Q with the block, okay, right? Okay. And it will do something, some other things also. We'll discuss that soon. Yes, you have a question.
So where you're saying that we can have two store operations at the same time.
Right.
So there might be two ways to implement this. One with a buffer, it starts putting the stores, or they might.
No, wait. Hang on. So you're saying each processor has a buffer?
I mean, I'm saying if both the stores come at the same time,
Yeah.
if one of them takes the ownership,
Yeah.
then the other one gets cancelled. Does it wait? How
No. It doesn't get cancelled as such. There are many ways to implement that. One possibility could be that in the directory controller, you could have a queue of pending requests, okay, which will be popped out one by one. To simplify matters, directory controller, the other option is the directory controller could say that, well, there is a request currently going on. I can't serve this request. It can negatively acknowledge queue, saying that please retry later. All right. So eventually it will succeed, but negative acknowledgement retries can lead to live lock and starvation. So you have to be careful. Yeah. So there are many possible ways to implement it. We are not getting into those details. Okay, all right. Okay, so the other invariant that we need to implement is that if a cache block is not in M state in any processor, memory must provide the block to the requester. That should be obvious because memory is the owner of the block. Okay, all right. Which means memory must be updated when a block transitions from M to S state. So let's try to understand this. Okay. So, so let's say that P has done a store. Okay, all right, has done a store to X. Okay. So currently P is having the block containing X in M state. All right. Now Q does a load of X. Okay. So what will we do? Let's assume that we have a directory. So Q will send a message to the corresponding directory, which will look up the directory entry and say that P is the owner. So the request will be forwarded to the P, so forwarded to P. So let's say I'll mark the directory controller as DC. So DC will send, Q will send a GET request to DC. DC will forward it to the owner by looking up the directory. And P will respond here with a put. All right. Now, what is going to be the state of the block in Q? It's not modified clearly. Okay, it's a clean block. Okay, right. So we need to cook up a state. So that's normally called a shared state. All right. Yes. What is going to be the state of P? It can't be modified anymore because P is not the sole owner of this block anymore. So what is normally done is that it's demoted to S. So P and Q are now shares. Okay, and of course directory will note that P and Q are now shares. Okay, all right. Now the question is, what happens if R does a load now? Load X. It goes to the directory controller. Directory controller says there is no owner currently. There are two processors sharing this block. Okay. So then why don't you pick it up from the shared cache? Unfortunately, shared cache does not have the up-to-date copy of the block because this guy did not notify the shared cache with the up-to-date copy. Okay. So that's what is mentioned here. Okay, right? That memory must be updated when a block transitions from M to S state. Okay. The other option could be that you could designate one of these P and Q as an owner. Okay, all right. And in that case, this will also be forwarded to the owner. One of these. Okay, you could elect an owner, and it will provide the correct block. But that would require an unnecessary hop through the interconnect, adding to the critical path of R. Okay. So you are better off updating the shared cache data when you transition from S state so that this guy can directly respond with a put. Okay. All right. So that's the meaning of this particular statement. Okay. That memory must be updated when a block transitions from M to S state. Okay. No, we have just disallowed that, right? We can't have that anymore because that's what we discussed here right now. Okay, right? Yeah. So in this particular case, what will happen is that Q will become M, this will become invalid. Okay, right? It will have to give up the block completely. Yeah. So note that a transition from M to I always updates memory in systems with write-back caches. These are normal write-back operations. By M to I don't mean this one. I mean you're just evicting the block. Okay. In this particular case, of course, memory will not be updated because Q will be responsible for updating the memory because it will inherit the ownership from P. Okay. Most of the implementations of a coherence protocol, I should say unfortunately, deals with uncommon cases and races. Okay. What we have discussed so far are the simple common cases. And the coherence protocol becomes complex because of these uncommon cases and races, which we'll not be discussing here. Okay. All right. But I just wanted you to introduce, you to be introduced to the basic protocol mechanisms. All right. So one small point here that is typically a distinction is made between invalidation and update. We have already seen how invalidations can maintain coherence by invalidating copies when a store happens. So you can also update the copies when a store happens. That's also possible. Okay. This dictates two classes of protocols and decides what action should be taken on a store. Invalidation-based protocols invalidate sharers when a store misappears. Update-based protocols update the sharer caches with the new value on a store. Okay? So instead of invalidating them, you just update the new value to all the caches. All right? Advantage of update-based protocols is that sharers continue to hit in the cache, while in invalidation-based protocols, sharers will miss next time they try to access the line. All right? Advantage of invalidation-based protocols, only store misses go on bus, and subsequent stores to the same line are cache hits. This is extremely important because you can do small updates to a wide cache block. Okay? And every such update will go on the interconnect, consuming bandwidth. And this is one of the primary reasons why invalidation-based protocols are preferred. In fact, that has become the de facto today. Okay? Nobody implements an update-based protocol. All right? There are other problems, other technical reasons why update-based protocols are not implemented, which we will not discuss here. But this is the primary reason why. Okay? Bandwidth reason, that stores can flood your interconnect completely. All right, so we'll spend a bit of time, again, going back to the software side and understanding some of the prevailing sharing patterns that you typically see in software. Okay. Two of them are producer-consumer and migratory sharing. So let's try to understand what they are. So as the name suggests, in producer-consumer, one thread produces a value and the other thread consumes it. All right? Other threads consume it. So there could be multiple threads consuming a value. So here's an example. Let's suppose flag is 0 initially. So T1 and T2 to Tk are threads. T1 says x equal to y and then sets flag equal to 1. Everything here is shared. Remember that. All variables are shared. T2 to Tk continue to loop on flag until it becomes 1 and then uses x. So this is an example of a producer-consumer sharing where T1 is the producer, which is producing x with a value, and T2 to Tk are consuming x. All right? In fact, if you look at the flag variable, that's also being produced by T1, consumed by T2 to Tk. Okay. All right? Clear? Producer-consumer sharing. Okay. And you can imagine that, I have said x equal to y here. Instead, I could say x equal to, g of y, which could be a complex function evaluated by T1. Results are consumed by T2 to Tk. Okay, all right? And they can further compute on the value. What is migratory pattern? Each thread reads and writes to a shared variable in sequence. That's called migratory pattern. Okay. Why is it called migratory? Well, we'll see very soon why it is called migratory. Here's an example. So assume I is in the range 1 to k. Flag is 1 initially. So we have T1 to Tk threads. And Ti says while flag is not equal to I, just keeps looping. All right? So it waits until flag becomes I, and then says x equal to f of x, and then increments flag. Okay. So if you look at what's happening here, focus on the variable x. Okay. So a particular thread will read x, compute f on that, write to x, and then the next thread will pick up x, read x, write to x, and so on. So x will essentially be read and written to by each thread in sequence, one by one. Okay, so that fits our definition of migratory sharing. Okay, all right? So let's try to understand why it is called migratory. Okay. And related to that, there is a concern called migratory handoff, which we'll also discuss. So so now we can succinctly represent the sequence of operations that a particular system will do for a variable to qualify as a migratory sharing pattern variable. So this sequence here, R0, W0, R1, W1, R2, W2, R3, W3, and so on, essentially what it means is that R0 means that processor 0 is doing a read to a particular variable. So the variable concerned is same here. Okay. W0 means that the same processor is doing a write, that is P0 is doing a write to the same variable. Then R1 means P1 is doing a read to the variable. Then W1 means P1 is doing a write to the variable, and so on. Okay, all right. So what is going to happen? So let's see. So P0, let's suppose that this particular variable that is being accessed is not in the cache of any of the processors. Okay, all right. So P0 wants to read this variable. So it will send a get to the directory controller. Directory controller will read it from the shared cache, send it back. All right. So P0 becomes a sharer now. That's marked in the directory. Okay. Now P0 wants to do a write. Okay. So what it sends is called an upgrade. What does it mean? Well, it means that P0 has the block. It doesn't need the block. It just needs a permission to modify the block. Okay. So it just wants to upgrade its status from S to M. Okay. All right. So it sends an upgrade, and the directory controller sends back an upgrade acknowledgement. Okay. In this particular case, there is no sharer, nothing to be done. And we can suppress the upgrade. We'll talk about that. Okay. All right. Because it seems a bit stupid that, P0 has the block, there are no sharers. Why seek a permission? Permission, you should be able to write it, right? Okay. Anyway, so now it becomes M. Now P1 wants to read. Okay. So it sends a get. Right? Okay. The directory controller figures out that this is the owner. It will forward the get. P0 will respond directly with a put to P1 and also send a special write back, which is normally called a sharing write back to the directory controller, because we said whenever somebody transitions from M to S, must update the shared cache. So both will now become S. Okay. And then it will do an upgrade. Now there is a sharer which needs to be invalidated. Okay. So directory controller will send an inval, right? And P0 will also, directory controller will also send an upgrade acknowledgement here. This is a bit special, which will encode that P1 must wait for one invalidation acknowledgement to arrive before it can do a modification. P0 will send the invalac here. And the block will become M. Okay. This will become I. So the block migrates from one processor to another in sequence. And that's where the name comes from, migratory sharing. All right. Now, as you have noticed here, every time a processor does a read in this sequence, you have to do a sharing write back to the next level of the shared cache. Okay, all right. That unnecessarily consumes bandwidth, which we must avoid if we can. Okay, all right. And that's actually easy to avoid. Solution is that you add an owner state, which is different from the M state in the caches. That is, so instead of writing this back, you say that, well, P1 has become the new owner, and the owner is responsible for writing the block back when it evicts the block from the cache. Okay. Then you can suppress all these sharing writebacks, because the ownership will now trickle through the sequence, and ultimately whoever evicts the block will write it back. Okay, all right. So sorry, second. No, not latency, bandwidth. Writebacks are not in the critical path. Well, in this particular case, you have to go to this processor anyway for P1. Yeah. So it doesn't save anything actually in terms of latency. Critical path remains unchanged. Okay. All right. Yeah. Yeah, so this is specific to migratory sharing, and this W0 to R1, W1 to R2, this is called a migratory handoff. Okay, you're handing off the migratory block to the next processor, all right? So ownership can shift along the migratory chain, so that will save the write back. So now let's summarize the states of the cache line. Invalid, as you can understand, the block is not in the cache, all right? So that's where the block starts off its life. It can become shared. We have already seen it here, that when it is shared by, when it is cached by at least one processor in clean state. It can be modified or dirty, or M. And there are two additional states, clean exclusive, or E, which we'll define, and an own state, or O. The own state we have just defined in the last slide, but we'll formalize that here further. Now, every processor does not support all these 5 states. It can support a subset. Okay? So what is this E state? So any question on the MS and I states? Are they clear? Okay. So E state is equivalent to M in the sense that the line has permission to write without telling anybody, all right? But in E state, the line is not yet modified, and the copy in memory is same as in cache. So that's the difference with the M state, where in M state, the block has already been modified, and the memory copy is out of date, all right? If someone else requests the line, the memory will provide the line after querying the E state holder. Okay, so from the memory's perspective, since there is no way for it to know when a block can transition from E to M state, because a transition from E to M state doesn't generate any traffic at all, if a block is in E state, the memory has to query the cache, asking, did you modify it? If yes, please provide the copy. Okay, all right? So that's what this statement says, that if someone else requests the line, the memory will provide the line after querying the E state holder, because the E state holder may now have been promoted to M by doing a write silently. Okay, all right? So there is no way for the memory to know that. So in that particular case, the owner will also provide a copy, and that will overrule the memory's copy. Okay. So that's your E state. Any question? So that will suppress this first upgrade that we did, because when you do a get, the directory controller will send the block in E state to P0. And now, when it wants to write, it can just do the write without asking anybody. Okay, all right? So it will transition from E to M automatically. There are bad things about E state also that should be clear here, that instead of E state, if the block was given in S state, the other requester could be supplied the block faster if the block hasn't yet been modified. Okay, so there are pros and cons of having an E state, but today most processors support an E state. What is the O state? Here, memory is not responsible for servicing the requests to the line. The owner must supply the line. So this is like M state, but O state blocks do not have write permission. So you must ask for permission to write in O state. That's the distinction between M state. In M state, you are the exclusive owner, you have write permission. In O state, you are the owner, which means you should supply the block, but you don't have write permission. Okay. So to go from O to M, you must have to generate an upgrade request. Okay. All right. All right. So by now, probably you may have noticed that if we didn't have any stores, we wouldn't require a cache coherence protocol. If we just had reads, everybody could read. There is no modification. Everybody could read concurrently without any control, right? And we have coherence protocols because we want to modify data. Okay. So let's look at the stores a bit more closely. So there are 3 situations at the time a store issues from a processor. And the line is not in the cache. That is, a processor wants to do a store, it looks at the cache. One possibility is that the line is not in the cache. Second possibility is that the line is in the cache in S state. Third possibility is that the line is in the cache in one of M, E, or O states. Okay, so these are the 3 possibilities that can arise. If the line is in I state, the store generates a read exclusive request on the bus and gets the line in M state, all right? So sometimes that's also called a getX by the terminology we are using here. The point is that it's an exclusive request asking for exclusive permission for the block, okay? If the line is in S or O state, that means the processor only has read permission for that line. The store generates an upgrade request on the bus, and the upgrade acknowledgement gives it the right permission. This is a dataless transaction. It doesn't have any data, it's just a permission saying that you can go ahead and do whatever you want to do. Of course, in M state, a store doesn't generate any transaction at all. It can do it silently, okay, all right? M and E state, okay. All right, so now we can take a look at one of the protocols which is possibly not implemented in any machine. It's purely for educational purpose. As the name suggests, now we can probably see what it means to say an MSI protocol. It supports 3 states, M, S, and I. It doesn't support O and E states. It forms the foundation of invalidation-based write-back protocols, assumes only 3 supported cache line states, I, S, and M. There may be multiple processors caching the line in S state. We have already seen that. That's the meaning of the S state. There must be exactly one processor caching a line in M state, and it's the owner of the line. That's the definition of the owner. If none of the caches have the line, memory must have the most up-to-date copy of the line. So these are the 3 basic invariants that we must maintain in this protocol. And this is what it looks like. I'll quickly tell you how to read this diagram. This is a state transition diagram. This state machine executes for every cache block in the system, all right? So individual cache block will have this state machine executed, which means individual cache blocks may be in different possible states, okay? So for a particular cache block, it starts off, it starts off in the I state, meaning that it is not in the cache. If it wants to do a read that's written as processor read, it will generate a bus read transaction, okay, and transition to S state when it gets the block. If it wants to do a write, that's processor write, generates a bus read exclusive transaction and goes to M state when it gets the block. In S state, it can do read without generating any transaction, okay. If it observes some other processor doing a bus read, it can stay in S state without moving. In the S state, if it wants to do a write, it will generate an upgrade, go to M state. In the S state, if it observes that somebody else is doing a bus read X or upgrade, it will invalidate itself and go back to I state. Also in S state, if it evicts the block, it will not generate any transaction on the bus because it's a clean block and go to I state. In M state, it can do read and write without telling anybody. While in M state, if it sees a bus read from somebody else, it is the owner, it must produce the block, that is, it flushes the block on the bus, the requester will pick it up, and this guy will go to S state, okay, it will demote itself. And in M state, if it sees a bus read X from somebody else, it is still responsible for providing the block, it flushes the block on the bus, but it will move itself to I state because we cannot have multiple processors in M state, that's not possible. Also in this state, if it evicts the block, it must generate a write back because this is the most up-to-date copy of the block and will go to I state. So that's how you have to read the transition diagram. This is the MSI protocol. You should go back and look at it further. Let's quickly run over an example. So this is a sequence of operations. P0 reads X, P1 reads X, P1 writes X, P0 reads X, P2 reads X, P3 writes X. So let's see what are the actions an MSI protocol will take. Let's assume the state of the cache line containing the address of X is I in all processors to begin with, okay? So P0 reads X, which means P0 will generate a bus read. Memory will provide the line because nobody is owner at this point, memory is the owner. P0 puts the line in S state. Then P1 wants to read X, so it will generate a bus read. Again, memory will provide the line because there is no owner. P1 puts the line in S state. Then P1 wants to write X, so it generates a bus upgrade. P0 will snoop and invalidate the line because we can't have multiple processors in M state. Memory does not respond. P1 sets the state of the line to M. Then P0 will read X, so it will generate bus read. P1 flushes the line and goes to S state. Why P1 flushes the line? Well, because P1 is the owner. It has the block in M state. P0 puts the line in S state, and memory writes back. Okay, because you have to write back because you're going from M to S. Okay. P2 generates bus read because P2 wanted to read. Memory provides a line because in this particular case, all processors are in S state, and whoever is having the block. So memory will provide the line. P2 puts the line in S state. And finally, P3 wanted to write, so it will generate a bus read X because it doesn't have the line at all. P0, P1, P2 all will snoop and invalidate because all have the block in the S state. Memory provides the line. P3 puts the line in M state and becomes the new owner. Okay, all right. So that's the transition. You should go back and look at this example, look at the transition diagram and see if they match. That should be helpful. Now, let's introduce the E state, which gives us a MESI protocol. All right. The most popular invalidation-based protocol, for example, it appears in all Intel Xeon multiprocessors. Why need the E state? We have defined the E state. I have also mentioned. So here it's written. The MSI protocol requires 2 transactions to go from I to M. We have seen that. I to first S, you do a get and then do an upgrade. Okay, right? So you can suppress the upgrade if you have an I state. Bus read followed by bus upgrade. Save on transaction by having memory controller respond to the first bus read with E state if there is no other sharer in the system. How do you know if there are no other sharers in the system? Well, that's not very easy to know if you don't have a directory. Okay. So in the old system, what used to happen is that in a small scale machine, there used to be a dedicated control wire that gets asserted by a sharer. So it's a wired OR line. Anybody asserts, the line goes high. Okay, all right. So then you know that there is a sharer. Okay, all right. Processor can write to a line in E state silently. So we have already said that. Okay. So this is so I'll not go and show you the MESI transition because there isn't much to show actually, because what you have to do is you introduce the E state in this, and essentially you'll have the transition from E to I to E, E to S, E to M and all. So you can add those by just looking at the definition of the E state that we have just mentioned here. Okay. So I'll just go over an example that will show you what it looks like. So let's say we have P0 reads X, P0 writes X, P1 reads X, P1 writes X. Okay. So P0 generates a bus read because it wanted to read. Memory provides line. P0 puts the line in cache in E state. So that's the difference compared to an MSI protocol. In an MSI protocol, you would put it in the S state. Okay. Now P0 writes X, so it can do it silently. It goes to M state, doesn't tell anybody. All right. And P1 reads X, so P1 generates bus read. P0 is the owner, generates the line. P1 puts the line in cache in S state. P0 also transitions to S state. The rest is going to be same as MSI. All right. Here's another example. P0 reads X, P1 reads X. So this will actually bring out the downside of having an E state. Okay, all right. So P0 generates a bus read. Memory provides line. P0 puts the line in cache in E state. That's same as the above. Now P1 generates bus read. Memory provides line. P1 puts the line in cache in S state. P0 also transitions to S state. Now here, what you could have done instead of memory providing the line, you could ask P0 to provide the line because it's in E state. Okay, and that's called cache-to-cache sharing. However, this is not a preferred way of doing things because you don't want to interfere into P0's cache too much. Okay, because it may be doing its own cache accesses, which will take away bandwidth from that. Okay. And the rest is going to be same as MSI. Memory operation could be a read or a load, or a write, or a store, or a read, modify, write. Read, modify, write means it's a single operation which will read a piece of data, change it in some way, and write it to memory. Okay, all right? So that's a read, modify, write. And each one of these is assumed to take place atomically. That is, you cannot further break down a read Okay, you cannot further break down a write. You cannot further break down a read, modify, write. So a memory operation is an atomic unit. You cannot break it down any further. All right. So that's sort of an axiom that we're going to assume. A memory operation is said to issue when it leaves the issue queue. You have seen the issue queue in processors, am I right? Right? Okay, good. And looks up the cache. So that's when a memory operation is said to issue. A memory operation is said to perform with respect to a processor when a processor can tell that from other issued memory operations. What does it mean? That means, let's say a processor does a write to x. Let's say it says x equal to 2. And then it reads x. By looking at the value of x, it can figure out whether the write performed or not. For example, if it gets the value 2, that means the write actually performed. If it doesn't get the value 2 but gets the old value, that means the write did not perform. Okay, all right. So that's what it means. Okay, all right. A read is said to perform with respect to a processor when subsequent writes issued by that processor cannot affect the returned read value. Okay. So let's say I read a value of x, okay, and the read is said to perform if the value returned by the read cannot be changed by a subsequent write. Okay, that's what it means. All right. That means the read has already been performed. You can't change its return value any further. Okay. A write is said to perform with respect to a processor when a subsequent read from that processor to the same address returns the new value. That's what I just mentioned. Okay, all right. So one thing to notice here is that we're talking about just a single processor here. Okay. We haven't yet said something like a write is said to perform with respect to a set of processors. We haven't yet said that. Okay. That's a far more difficult notion of things. Okay, we'll get to that. A memory operation is said to complete when it has performed with respect to all processors in the system. All right. So now for individual processor, we can test if a memory operation has performed. And then if every processor says yes, that means the memory operation has performed with respect to the entire system. All right. Now, how do you order memory operations? Let's assume that there is a single shared memory and no caches. Let's simplify our life. Okay. Memory operations complete in shared memory when they access the corresponding memory locations. Okay. That should be obvious. Operations from the same processor complete in program order. I'll soon define what is meant by program order, but for now, intuitively, what I mean is that if you read a program, instruction by instruction, that is a program order. Okay, all right. This imposes a partial order among the memory operations. Operations from different processors are interleaved in such a way that the program order is maintained for each processor. All right. So that means if I take these two statements from here and these two from here, I can interleave them in arbitrary fashion. For example, I could say x equal to 2, x equal to 5, z equal to y, y equal to x. That's one possible total order. I just interleave the partial orders. All right. Partial orders cannot be violated. That's important. All right. So that imposes a total order on the set of accesses. And as you can see, many possible total orders exist. Okay. Because, for example, you can take these pair of accesses from here and here, and you can interleave in many different ways. And in fact, you can compute combinatorially how many you can do. Okay. So here's an example. Let's say we have two processors, P0 and P1. P0 is doing those three accesses, x equal to 8, u equal to y, v equal to 9. P1 is r equal to 5, y equal to 4, t equal to v. So one possible total order could be this. I have interleaved them, honoring the partial order. Okay, all right. Another legal total order could be this. Again, notice that within the total order, I never violate these individual partial orders. That is, x equal to 8, e equal to y, v equal to 9 is still maintained in this total order, in both of these. Similarly, r equal to 5, y equal to 4, t equal to v. Okay, all right. So now we are ready to define last. Last means the most recent in some total order. Okay, all right. There is still some fuzziness because there could be millions of total orders possible. Okay, all right. But given a total order, I can define what last means. Okay, that's easy. A system is coherent if reads get the last written value in the total order. Okay. What it means is that you have run a program, and let's say you have machinery to collect the total order of the memory accesses, and you find that your machine has returned a certain value of a variable which doesn't conform to that total order. That means the machine is not coherent. Okay. All right, that's what it means. Okay. All processors see writes to a location in the same order. So these two conditions must hold together. Okay. All right, so reads get the last written value in the total order, and all processors see writes to a location in the same order. Okay. So I'll clarify the last one soon. So here's a formal definition of cache coherence. A memory system is coherent if the values returned by reads to a memory location during an execution of a program are such that all operations to that location can form a hypothetical total order that is consistent with the serial order and has the following two properties. Number one, operations issued by any particular processor perform according to the issue order. You can't reorder those. Two, the value returned by a read is the value returned to that location by the last write in the total order. Okay. Then the system is coherent. What is important is that it never says how quickly this written value will propagate. But all it says is that if you do a write, if you do a read, it must return the last performed writes value. Okay, that's all you have to guarantee. All right, it doesn't have to be instantaneous. Two necessary features that follow from the above. One is write propagation, that is writes must eventually become visible to all processors. If this breaks, you can easily see that the machine could be out of coherence. Write serialization, every processor should see writes to a location in the same order. That is, if I see W1 before W2, where these are two writes to a particular location, you should not see W2 before W1. Okay, all right, so that's what it means. So the global order of writes must be maintained across the system. Okay, I'm not telling you how to do that. All right, I'm giving you some abstract definitions because we'll be using these in the next 45 minutes or so. All right, so let me switch the slides. So what we'll discuss now is something called memory consistency models. One thing that you should keep in mind is that often this is confused, that these models are completely orthogonal to cache coherence. That is, a machine could be perfectly coherent, but may not conform to certain models of memory consistency. Okay, all right, so these are not really interlinked. And if you want me to demystify this a bit, it means architectural support for improved understanding of program outcome. Okay. We'll see what it really means, because you probably think that, well, given a program, if you run it, why shouldn't I understand what the outcome is going to be and what is there to understand more, right? So we'll see what is there. Okay, so we'll first try to see what are these models and why they're needed. And I'll introduce you to two models. One is sequential consistency model, which is the most intuitive model, and one relaxed consistency model, and that is total store order. Okay, so we'll stop there. So what are these models and why? A parallel program can have multiple possible outputs. What? Really? Do you believe that? Yeah? I don't see too many people nodding. Okay, let's take an example. Again, here all variables are shared. Okay, so T0 says x equal to 1, T1 says y equal to x, print y. What does T1 print if the initial value of x is 0? 0? That's all? So it depends on how T0 and T1 actually get interleaved, right? When they get scheduled and so on. Okay, so it could be 0 or 1. Both are possible, but nothing else is possible. Okay, is that clear? Okay, yeah. But this is a very well-behaved program, I would say. There are only two possibilities, 0 and 1. Okay. Not too many programs are like that. I'm sorry. Now, the coherence protocol is not enough to completely specify the outputs of a parallel program. Okay. You can see it here, right? A machine can be perfectly coherent, but you run this program multiple times. Sometimes you'll get 0, sometimes you'll get 1. Okay, all right? So, coherence protocol only provides the foundation to reason about the legal outcomes of accesses to the same memory location. Okay. So, if I have a stream of accesses going to the same memory location, it can tell me what is going to be the outcome of the reads to that location, okay, given that stream. Memory consistency models tell us the possible outcomes arising from legal ordering of accesses to all memory locations. Okay, all right. So, that's what it actually offers. So, without any specified ordering constraints, all possible outputs could be legal. By legal, I mean correct. So, now I am, we are probably going to kill me now. I'm telling you that you write a program and 100 possible outputs are all correct. So, nothing is wrong. Let's take this program. Okay, so we have two threads T0 and T1, and there are two shared variables A and B. T0 says A equal to 1, print B. T1 says B equal to 1, print A. The question is, what do T0 and T1 print if the initial values of A and B are 0? What do you think? Sorry? 0, 1, is that the only possible outcome? 0, 1, 1, 0? 1, 1, all three are possible. 0, 0 is not possible? Why not? Sorry? Okay, so we are assuming that within a thread, we are not allowed to reorder these statements. Why not? A equal to 1, print B, these are two totally different accesses. One is reading from B, other one is storing to A. You just read that the processors mess up everything today, right, inside them. They reorder things madly. So that could also be possible, right? 0, 0, no? So, sorry? I'll just reorder print B and A equal to 1. These are independent, right? There is no dependence between these. Sorry, second?
So you're first modifying one variable, then you're putting the other variable.
Yeah.
0, 0 something.
Well, I'll reorder print B and A equal to 1, print A and B equal to 1. No, it's not a different case. I mean, you have just learned that out of order issue processors reorder instructions, right, if they're independent. A equal to 1 is a store to A. Print B is roughly a load from B. You can think about it that way, right? They can be? They can be reordered, right? They are independent, right? So 0, 0 could be possible also, right? So all four possibilities are there, okay? And what I'm saying is that they are all correct. Okay? So that is where things start getting fuzzy. So given a memory consistency model, only a subset of outcomes is possible. And it is important for a programmer to know this subset. Okay. So for example, certain memory consistency models will not allow the outcome 0, 0 for this program. Okay. But it may allow 0, 1, 1, 0, and 1, 1. And for the programmer, it's important to know what is allowed and what is not allowed, so that he or she can debug his or her program, okay, and so on. A shared memory machine advertises the supported memory consistency model. It's a contract with the writers of parallel applications and system software. It's a contract in the sense that I'll tell you what memory consistency model I'm going to implement as a hardware designer, and you have to write your program keeping that in mind so that you get your expected answers. Okay, all right? So that's the contract. Okay. So usually the programmer wants one specific output from a correct program, right? So that makes sense. So let's suppose that the programmer wants T1 to print 1 in the following program. We have seen that 0 or 1 both could be printed. What will you do? Well, scheduler is not in your hand. It's the kernel scheduler which will schedule the threads in arbitrary order. You can't do anything. how to change this program to make sure that every time you run it, T1 prints 1. What will you do? Do you need a semaphore? Some sort of? Signal. Can you be a bit more specific? We're talking about C language here, let's say. You add a flag? Yeah, right, precisely so. So as simple as that. I just need to make sure that T0 executes before T1. That's good enough, right? So, so this could be one possible solution, that you add a flag here set to 1. T1 will loop on the flag and then do this. But I say that it may seem that the synchronization can guarantee such an output, flag equal to 0 initially. Okay, right? Why it may? It should always be correct, right? What can go wrong? Unfortunately, these two are totally independent stores, x equal to 1 and flag equal to 1. I can reorder them, right? Welcome. So, so what if flag equal to 1 is made visible to other processes before x equal to 1 becomes visible? So it's a big problem, right? Now it seems that I can't write a correct program at all. It's not that bad. So this can happen either by compiler reordering or hardware reordering, but there is a catch. You must honor something called precise exception, which roughly means that I should not land up in a situation where I have committed flag equal to 1 before x equal to 1, and x equal to 1 lands up in a page fault. I can't roll back now. I have already committed flag equal to 1, but I should roll back because page faults should be restartable exceptions. Okay, all right? Which means I still have to be a bit careful while doing these things. Okay. And this is roughly guaranteed if I make sure that I commit in order. Okay. But that still doesn't say that flag 1 cannot execute before x equal to 1 and can make the value visible to others. Okay. All right. So somebody designing a multiprocessor will have to be very, very careful about these subtle things. Okay. Committing in order, if that becomes decoupled with making things visible to the external world, things may actually break. Okay. All right. This is quite possible given that two stores are going to two different addresses. We have already said that. Okay, all right. So a memory consistency model is a set of rules that specify the set of allowed orderings between all memory accesses. Okay? And we'll see some of these rules of a few models very soon. A multiprocessor normally advertises the supported memory consistency model. This essentially tells the programmer what the possible correct outcomes of a program could be when run on that machine. All right? A multiprocessor is said to implement a memory consistency model when it adheres to the set of ordering rules specified by that model. Okay? Now, many memory consistency models exist. Each model represents a unique point in the three-dimensional space spanned by ease of programming, implementation complexity, and performance/energy. So essentially, every model is a trade-off between these three things. Okay. A model can make programming very easy, which means you run the program, you get your intuitive result. Okay. You don't have to worry about anything. Okay. On the other hand, a model could make programming very difficult in the sense that to get your expected results, you have to put a lot of blood and sweat, whereas implementation complexity may actually go down for the processor. All right? So there are these three things that play together to define a memory consistency model. Sequential consistency is the most intuitive one, and we'll focus on it first. And if you ask me, I would say this gives you the easiest avenue to program a machine because it gives you the intuitive result. Implementation complexity is iota more than what your out-of-order processors have today. Okay? It gives you more or less same performance as an out-of-order engine that you have seen. Okay, all right? So we'll see actually how to implement sequential consistency on top of a regular processor. So what are the rules of SC? First one that I mentioned here is true for everybody, achieved by interleaving accesses from different processors. We have seen that. You can interleave the accesses from different processors in whatever way you want. Okay, all right? Now, this is specific to SC. The accesses from the same processor are presented to the memory system in program order. That rule, if followed, will give you the sequential consistency. We haven't yet defined what program order is. We'll define that. Okay. So this is roughly same as, keeping this order same, keeping this order same, interleave them. Okay, all right? So a legal SC ordering is equivalent to the total order obtained by a randomly moving switch connecting the processors to memory. So, so here you can see that there are 4 processors. There is a memory module here. There is a switch which will randomly pick the next processor to take the next request from. And it picks the next access from a randomly chosen processor. So for example, first it does a read A from P2. Then it could do write X from P1. Then it could do read Y from P3. Then it could do write A from P0. So this is the total order that you are going to get. The point is that within the request set of P0, it's never going to reorder anything. Okay, it's going to, you can think of it this way, that each processor has a FIFO queue of requests, and the switch will pick the head every time. Okay, but which head it will pick is random. All right. So all the possible total orders that you're going to get by doing this are sequentially consistent. Okay. So this is the definition provided by Leslie Lamport. You know about him? Leslie Lamport? Somebody? Raise hand. Leslie Lamport? How do you know? Okay, and? Distributed systems and, no, I mean, in what context?
Okay, logical clocks, Lamport's logical clocks.
Lamport clock, okay, all right. Nobody else, that's interesting. No. He extended something related to that, but not dining philosophers. Lamport's mutual exclusion, you don't know? What is it called? No, there is an algorithm that Lamport proposed for mutual exclusion. Beckery? Ah, right. So anyway, so Lamport won the Turing Award a few years ago for his contributions to distributed systems. Do you use LaTeX? Yes? Huh? That's also from Lamport. Okay. All right. LaTeX stands for Lamport's Tech. Okay, yes, Donald Knuth contributed hugely to tech, that is right. So Lamport contributed immensely to memory models also, and this is the original definition that Lamport gave for sequential consistency. A multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order, and the operations of each individual processor appear in the sequence in the order specified by its program. That's exactly what we mentioned, we showed with the switch, okay, right? Okay. So what is program order? So we need to now fix this thing, right? So one thing that is important is any legal reordering is allowed. Okay, that's very important because it cannot be that whatever the compiler presents to me, the instruction sequence is the program order. Then it's big trouble implementing these things efficiently. Okay, so any legal reordering is allowed. Then what is the program order? Well, the program order is the order of instructions from a sequential piece of code where programmer's intuition is preserved. Now you'll tell me, come on, you're playing with words. Well, the order must produce the result a programmer expects. And can out-of-order execution violate program order? No, it cannot. all microprocessors commit instructions in order, and that is where the state becomes visible. And for modern microprocessors, the program order is really the commit order. And that's what we're going to assume, all right? The order in which you commit instructions is the program order, which means you can do legal reorderings inside the processor. You can still carry your mess around of the processor as long as you commit in order. I'm good, all right? Okay. So example, again, the old one that we discussed in the last set of slides. This is one possible total order where you can see that the partial order is maintained, okay? Another legal total order could be this. All such total orders are allowed by sequential consistency, okay? A multiprocessor implementing sequential consistency can produce an output conforming to any of these total orders, okay? All these possible outputs are correct for a sequentially consistent multiprocessor, okay? So if you have written your program so that it can produce multiple outcomes, then all of these are correct. Like for example, if you look at that program, P0 and P1, it can have huge number of correct outcomes on a sequential consistent machine, okay? Can out of order execution violate SC? What's your take? Any hunch? Okay. Can? How?
It just takes the issue queue and
Okay, but it commits in order. Right. Okay, so how? Okay, all right, we'll look at an example. Yes, it can. You need extra logic to support sequential consistency on top of out-of-order execution. Fortunately, this logic is already there. We just need to leverage that. This logic is there for a different purpose. Let's consider a simple example and try to see how it can violate. Okay. All variables are 0 initially. So you have P0 equal to x equal, P0 doing x equal to w plus 1 and r equal to y plus 1. P1 is doing y equal to 2 and w equal to y plus 1. Okay? And I execute this program and I find that instructions commit in order with x equal to 4, r equal to 1, y equal to 2, w equal to 3. Have a look at it, think about it for a moment. Is this possible? Is this okay, this output? Y equal to 2 must be okay. How do you get x equal to 4? That means w must be 3. I don't know in what order they commit, but whenever it's scheduled, they commit in order. That's all I know. Is okay? Do you see any problem in this? Let's take x. How do you get x equal to 4? That means w must be 3, right? Right? That means P1 must have executed completely, right? Okay. So then how can you get r equal to 1? Sorry? Okay. Right, exactly. So in out of order engine, what may happen is that if you look at these two, x equal to w plus 1, r equal to y plus 1, if you translate them to any possible assembly language program, any ISA, you're going to get a bunch of totally independent instructions. Okay, right? They have absolutely nothing common in these two statements. So the processor is freely allowed to reorder them. Okay? So what may happen is that this load of y, so r equal to y plus 1 will have 3 instructions. Load y, increment, then stored to r. Okay, right? This load of y may execute before y equal to 2. We'll get a value 0. Okay? Cannot commit because we said that commit is going to be in order. Okay, all right? But now the increment can commit, the store can, increment can complete, the store can complete. all right? None of them can commit yet because this might still be pending, all right? So, so let's see exactly how, even with in-order commit, this can lead to a problem. So suppose the load that reads W takes a miss in the local cache of P naught, okay? And so W is not ready for a long time, all right? Okay, which means the chain of dependence that is originating from load of W, then W plus 1, then X equal to W plus 1, all are pending, all are waiting, okay? Therefore, X equal to W plus 1 cannot complete immediately. Eventually, W returns the value 3, okay, all right? Because while the load was in flight, P1 got scheduled, and Y equal to 2, W equal to Y plus 1 committed, so the new value of W became visible, and P naught brought back that value into the cache. Inside the microprocessor of P0, R equal to Y plus 1 completes but does not commit before X equal to W plus 1 and gets the old value of Y, possibly from cache, because Y could be in the cache, okay, right? Eventually, instructions commit in order with X equal to 4, R equal to 1, Y equal to 2, W equal to 3. So what the out of order engine does not know is that it needed to do something with this load of Y, which it executed speculatively. Okay. Otherwise, it did fine, absolutely fine. It followed out of order protocol, following the data flow, maintaining dependency, everything is okay. However, it just missed out this point that in the global order, a new value of Y has appeared while this load was waiting in the ROB to be committed. Okay, all right? We need to fix that. So, so first we need to, I'll show you a way to prove things which are not SC, a very nice way, before we go into fixing that. So you always start with partial orders, all right? So given this outcome, X equal to 4, R equal to 1, Y equal to 2, W equal to 3, what are the partial orders that you can infer? Okay, all right, so then let's do that first. So for P naught, we can infer that, so essentially we're going to assume that the partial order is maintained within a processor because we commit in order, that's given to us. So these partial orders are obvious. X equal to W plus 1 happens before, so this sign means happens before, R equal to Y plus 1. For P1, Y equal to 2 happens before W equal to Y plus 1, all right? So that's trivial, these two partial orders. Any question on this? This we derive from the given information that processors commit in order, okay, all right? Cross-thread orders that we can infer from the given output is that W equal to Y plus 1 must have happened before X equal to W plus 1, and that's why X got 4. There is no other way for X to get 4, okay, all right? Similarly, R equal to Y plus 1 must have happened before Y equal to 2 because there is no other way for R to get 1, okay? Now we can mix these partial orders to derive a total order, okay? So if you do that, you're going to get this. X equal to W plus 1 happens before R equal to Y plus 1. So this part is copied directly from here. Then I plug in R equal to Y plus 1 happens before Y equal to 2, taken from here. Y equal to 2 happens before W equal to Y plus 1, I take from here. And W equal to Y plus 1 happens before X equal to W plus 1, I take it from here. You get a cycle. Do you see that? It says X equal to W plus 1 happens before X equal to W plus 1. That's a violation of causality, okay? All right? So that means something must have been wrong with this output. It's not possible, okay? So this is how you normally prove something that violates SC given an outcome, okay? Given that it has validated SC, we need special support to guarantee SC in the presence of out-of-order instruction execution, and that's what we're going to understand next. Any questions so far? Yes? How do I get this? Yeah. So these partial order comes from the fact that X got a value 4, which means this must have executed, otherwise X cannot get a value 4. Similarly, this comes along because R got a value 1, that means this must have executed before Y got the new value. Okay, right? So, yes. Sorry, second. Yeah. Yeah, that's what I've said here. Yeah, right. In the total order. Yeah. Right. That's the partial order within a processor. Yeah. So one thing to be maintained in mind is that the system is still coherent. The coherence protocol has absolutely no bug in this. The writes were propagated eventually where it needed to be propagated. The only problem was with the out of order engine, which did not quote unquote roll back the speculatively executed load. Okay, all right. So before we go to the solution, let's look at one more example, our old one. P0 doing A equal to 1, print B, P1 doing B equal to 1, print A. Possible outcomes for an SC machine. By PA and PB here, I mean what is printed for A and B. Okay, all right. It's not the final value of A and B, because the final value of A and B are going to be 1 and 1. Okay, whatever you do. Okay, that's not going to change. So PA and PB signify what is printed for A and what is printed for B. So the first one is A prints 0. 0 is printed for A and 1 is printed for B. How do you get that? Well, you just need to make sure that B equal to 1 print A execute before A equal to 1 print B. Okay, then you're going to get this particular outcome. I'm just going to give you SC compliant interleavings, giving you possible outcomes. All right. Similarly, PAPB 1 0 is possible given this interleaving. Notice that in none of these I violate the partial order within P0 and P1. That's still maintained. Okay, it's just different total order. All right. Similarly, 1 1 you can get in two possible ways. I show it here. A equal to 1, B equal to 1, then print A, print B, or A equal to 1, B equal to 1, print B, print A. Okay, so you can go either way. You should convince yourself that 0 0 is not possible for SC. Okay, that's ruled out simply because we cannot violate the partial order here. Okay, within this, so 0 0 is not possible. All right. So for SC to be implemented, you require two basic requirements to be observed. Memory operations issued by a processor must become visible to others in program order. That's number one. Two, need to make sure that all processors see the same total order of memory operations. That is, in the previous example for 0 1 case, both P0 and P1 should see the same interleaving B equal to 1 print A equal to 1 print B. So if you go back here, all I'm saying is that here this interleaving of these operations must be observed exactly in the same order by both the processors, okay, for sequential consistency to be maintained. The tricky part is to make sure that writes become visible in the same order to all processors, because that's the most difficult part. It's a distributed system. Somebody is writing. You have to make sure that if there are two concurrent writes to two different addresses, you have to make sure that these two writes become visible to everybody in exactly the same order. Okay. So this is called write atomicity, as if each write is an atomic operation. So if that is the case, then you will see the writes in the same order across the entire system. Otherwise, two processors may end up using different values if they see two writes in different orders, okay, which may still be correct from the viewpoint of cache coherence, because the cache coherence is just responsible to ferry the right value correctly to all possible locations. It is not worried about ordering of two independent writes going to two different locations, okay. But this will violate sequential consistency. So let's take an example. Let's say A equal to 0 and B equal to 0 initially, and we have three processors here, P0, P1, P2. P0 says A equal to 1, P1 says while not A, B equal to 1, P2 says while not B, print A. All right. Question is, what should be printed? And if you follow the chain, you will see that a correct execution on an SC machine should print A equal to 1, right? Because A equal to 1 must happen before this can break this loop, and this can break the loop only after B equal to 1 happens, and that guarantees by transitivity that one should be printed here. Okay, all right. Now, let's think about how we can end up getting a 0 value printed. Okay, that could be interesting. So A equal to 0 will be printed only if right to A is not visible to P2. Why do I say that? Well, that simply means that the new value of A somehow did not reach P2. Coherence protocol says that it will eventually reach. But in this case, by the time the processor reached print equal to A, print A, it did not reach. Fine. Coherence protocol not to be blamed. It's fine. It says eventually it will get there. Okay. But write to A was visible to P1. Why? Because since it has come out of this loop and has set B equal to 1, because that's the only reason how P2 can proceed to printing A, that means P1 must have seen the new value of A. That's pretty clear, right? Okay. So this is an example where P1 and P2 see two writes in two different orders. And what are the writes? So A equal to 0 is possible if P1 sees the order A equal to 1 happening before B equal to 1, and P2 sees the order B equal to 1 happening before A equal to 1. That is, from the viewpoint of the whole system, the write A equal to 1 was not atomic. Do you see that? So P1 sees A equal to 1 before B equal to 1, and that's the reason why it broke the loop and went ahead and did this. Okay. P2 saw B equal to 1 before A equal to 1, and that's why it broke the loop but printed a value 0 here. That means by the time it saw B's value, the new value of B, did not see the new value of A. Okay, all right. So this is an example where SC is violated because we could not guarantee the write atomicity across the system. Okay. A pair of writes were seen in different orders by two different processors. Okay. So without write atomicity, P2 may proceed to print 0 with a stale value from its cache. For example, A could be in its cache, in P2's cache. Okay, all right. Any question on this example? Is this clear? How write atomicity can break sequential consistency? Okay. All right, so in summary, a program order from each processor creates a partial order among memory operations. Interleaving of these partial orders define a total order. Sequential consistency, one of many total orders. A multiprocessor is said to be SC if all executions on this machine are SC compliant. Now we'll look at how to implement SC. Okay. So MIPS R10K is an old processor from MIPS Technologies, which implemented sequential consistency. Okay, so that it dates back to mid-90s, pretty old. And this machine also implements all out-of-order machineries that you see today, register renaming, whatever the scheduling of out-of-order instructions, independent instructions, and so on. Okay. So it has all the machineries of out-of-order execution, and let's see how it actually built on top of that to implement sequential consistency. So out-of-order execution is allowed, and a proper recovery mechanism is invoked when a potential violation of total order is detected. Okay. So it's not like there is a piece of feature that always keeps track of this SC sufficient conditions. It's not like that. Only when a violation is detected, it will trigger the recovery. Okay, all right, and let's see what is that. The approach is somewhat conservative because the detection mechanism is far from ideal. The way it detects a violation could be improved by far. Okay, so that way it is a very conservative mechanism that it follows. A violation in the total order manifests through wrong values supplied by loads. We have already seen that. Okay. Loads execute potentially long before they commit. So the example that we have seen, exactly that's what happened. The value supplied by a load when it executes may get changed by some other thread before the load commits. And that's what we have to be careful about. If the load is allowed to commit the old value, this may violate SC. Note that this is still coherent. We have already seen an example. Okay, all right. So how to detect such loads? That's the number one question. All right. And the second question is, when you have detected such a load, how do you recover from such a violation? Okay. So I'll show you this entire mechanism through an example. So let's consider a load to address A in thread X. Okay. And when I say thread X, I assume that it runs on a different processor. Okay. So thread X runs on, let's say, processor X. Okay. The load executes at time t1 and gets a value v. All right. The load is yet to commit and stays in the ROB for the processor running X, because there could be instructions ahead of it which need to commit before the load can be committed. Another thread Y performs a store to address A, and I assume thread Y runs on processor Y. All right, so these are two independent processors. Performs a store to address A with a new value V prime at time t2. All right. At this point, an invalidation for A is sent to X, right? Has to be, because the directory will say that, well, processor X is a sharer for this particular variable, you should send an invalidation. So the invalidation goes and essentially will look up the cache, invalidate the cached copy of A. That's what normal cache coherence protocols will do. And the cache coherence protocol, whatever it does is correct. Okay, all right. We're going to do some extra work here. That is this. The invalidation searches the load queue for all matching loads. Remember that this load that processor X executed is still sitting in the load queue. All right, it's not yet committed. All right, and load queue entries are not freed until the load commits for various reasons. One of these is this. So if found a matching load, all instructions are cancelled starting from the oldest such load. Okay, these instructions will be refetched and re-executed. So if you do that, you are good, because now when the load executes, it will suffer a cache miss because that has been invalidated by the store, and will now the directory will forward this to the owner, which is Y, and Y will supply the new value V prime. Okay, all right. So fortunately, this support of searching the load queue is already there. Have you been taught about memory disambiguation in your out of order lectures? No, okay, don't worry about it then. So this particular facility to search the load queue for a particular address is already there in processors for a different reason. And here you can just leverage that. Okay. You don't have to add anything extra to it. Okay, all right. Now this part, this refetching and re-executing, can be further optimized. You could just re-execute them if you could keep track of the instructions which depend on this load. Okay, you could re-execute exactly that set. Or you could only re-execute all these instructions without refetching. That's also possible. But you need extra hardware to be able to do that. Okay, and again, today's processors already have those hardware to refetch or re-execute or only re-execute or whatever. Okay. So this is nothing extra that requires to be added. Okay. When an invalidation comes, the only thing is that it will now do an extra search on the load queue. It's essentially trigger that machinery which are already there. May consume a bit of extra power to do that, because these operations are expensive in terms of power, searching the load queue. But it will give you more or less the same performance. Okay. So you need to be careful about store commit a bit, because it is tempting to remove an in-flight store from the head of ROB to allow following instructions to commit. Because stores don't have any dependent instruction. So you might wonder, why should I keep a store at the top of the ROB? Just remove it so that other instructions can commit. Well, the problem is that this may violate sequential consistency. How? Consider this one. Again, the old example, A equal to 1 print B, B equal to 1 print A. Now, if you think that, well, A equal to 1 and B equal to 1 are at the top of the ROB of the two processors, remove them. They're in flight, they haven't yet completed. Now, we're in a situation where we may end up getting a result of 0, 0, which is in violation with SC, okay, right? So MIPS R10K keeps stores in ROB until they are complete, which is a big performance hog, unfortunately, but if you want to do SC, that's the only thing you can do. All right, so we'll spend a couple of minutes and then you can stretch for a longer period of time, relax. So we'll discuss something called relaxed models, just a couple of slides. Implementing SC requires complex hardware and verification efforts. So you have to search the load queue. Somebody has to verify that piece of controller which does that. Unfortunately, these violations are very rare. That's what is seen in typical parallel programs. Okay. So which essentially questions the necessity of doing this particular extra hardware check on an invalidation. Okay. So many processors today relax the consistency model to get rid of complex hardware and achieve some extra performance at the cost of making program reasoning a bit complex. So let's try to understand that part. So let's say we have this program. T0 says A equal to 1, B equal to 1, flag equal to 1. T1 waits on the flag. Let's say flag is 0 initially, then prints A and prints B. Okay, all right? So you can reorder the stores A and B without any problem. I can reorder these two. As long as they are not reordered with respect to flag equal to 1, I'm still going to get the correct result. Right? Okay? So cannot compromise on precise exception, however. When you reorder these two, you have to make sure that you can still roll back to a precise state if an exception occurs. So the point is that SC is too restrictive. Relaxing it does not always violate programmer's intuition. For example, here, I could reorder these two stores and still be happy. Okay, there is no problem. My outputs will still be correct here. Both will be printed as 1. Okay, all right. So there are 3 attributes of a relaxed model. System specification, which orders are preserved and which are not. So that's the part of the system specification of the model. If all program orders are not preserved, what support is provided, software and hardware, to enforce a particular order that the programmer wishes. For example, I may want a SC compliant outcome on such a machine. Okay, then how can I do that? Programmer's interface, set of rules, if followed, will lead to an execution as expected by the programmer, specified in terms of high-level language annotations and labels. Translation mechanism, how to translate programmer's annotation to hardware actions. So we'll see some of these, okay, in the next couple of slides. So I'll talk about one relaxed model, which is called the total store order, TSO, one of many relaxed models. TSO allows a load to bypass and commit earlier than an older incomplete store. So this is exactly what we just discussed, that you have a store pending on the top of ROB. Can I bypass it and commit a load, okay, which has already completed? Okay, and that's exactly what TSO offers. A blocked store at the head of the ROB can be removed, but remains in a FIFO store buffer, and subsequent instructions are allowed to commit bypassing the blocked store. Okay? Motivation can hide latency of store operations, because store operations should not be in the critical path, ideally, because nobody is waiting for the store to complete. There is no instruction that depends on a store. This is the only allowed reordering. That's very important to keep in mind. Only a load can bypass an older store and nothing else in TSO. For example, a load cannot bypass an older load. A store cannot bypass an older load, and a store cannot bypass an older store. These three are disallowed. The only thing that is allowed is a load can bypass an older store. All right? So TSO allows a load to bypass and commit earlier than an older incomplete store. As usual, precise exception must be guaranteed, meaning that a store at the head of the ROB can unblock the ROB only when it is guaranteed that the store cannot raise an exception. Okay? Easy to ascertain because a store can raise only page fault exceptions, which is a good thing. You can localize the exception, and a store is cleared of page fault exception as soon as it passes TLB lookup, because that's the point when you know that it cannot suffer a page fault exception any further as long as it completes the TLB lookup. Okay. So programmer's intuition is preserved in most cases, but not always. Let's look at a few examples. So our old example, A equal to 1, flag equal to 1, and in P1, while not flag, print A. That's preserved in TSO because you can't reorder these two in TSO. TSO doesn't allow stores to be reordered. Okay? So this is same as SC. A equal to 1, B equal to 1, P1 says print B, print A. These is also same as SC because you can't reorder these, you can't reorder these. Okay? Similarly here, in this example, you can't reorder anything, so it will be same as SC for TSO. Here, unfortunately, you can reorder. For example, TSO will allow print B to happen before A equal to 1 completes. Okay. So this program can violate SC under TSO and can produce an output of 0, 0. Okay, that's possible. And this is implemented in many Sun/Oracle UltraSpark microprocessors. TSO appeared in them for the first time. Of course, many variants of TSO today found in many processors. So the question now is that, let's say I want to take this program, this one here, which violates SC, and want to run on a TSO compliant machine and still get SC compliant output, meaning that I don't want 0, 0 to appear as an output. Okay, how do I do that? Okay. So this is required when porting a program from, say, MIPS R10K to a Spark processor platform. Okay. So the program which was running correctly on MIPS R10K should continue to run on a Spark machine correctly. But Spark machine supports a relaxed model, so certain programs may actually fail. Okay, right? So must ensure that a load cannot bypass an older store. So that's the problem order that we have to disallow now. Okay. So microprocessors provide fence instructions for this purpose. These are specialized instructions that can enforce this thing. Spark v9 specification provides a membar instruction, stands for memory barrier, of different flavors. So in this particular case, we only need to use one of these flavors, namely store to load fence, just before the load instruction. So let me show you how it looks like. So this is how it will be done. So we had A equal to 1 print B, B equal to 1 print A, and we want to make sure that print B cannot happen before A equal to 1. So we'll put a membar instruction of the type store load. Okay. All right, so this is how the flavor is mentioned. Similarly here. This will make sure that print B will not be allowed to issue until A equal to 1 completes. So the fence instruction will not allow graduation of a load until all stores before it graduates. If a fence instruction is not available, substituting the load by a read modify write also works, because a read modify write has a load as well as a store. So since TSO doesn't allow store to be bypassed over stores, then if you just replace this load here of B by a load store unsigned byte of Spark, this will also work. Okay, all right. A read modify write contains a store, and hence it cannot be reordered before an older store. That would violate TSO. That's all. Thank you for your patience. So I'll be outside. If you have more questions, we can discuss.